Hi boys and girls, welcome to a new IB Physics video. In this video, I'll talk about momentum and guide you through the textbook question on page 109. Before we start, let's have a look at the study guide from IBO so you know the expectation for you to do in momentum. The first one is the equation about rate change of momentum, which is basically the last one here. Second one is about the graph, impulse and force time diagram. That means if you got a force against time here and whatever the graph look like, and you should be able, you should know that the area under the line is representing the impulse change of momentum here. The third one here is talking about conservation of linear momentum. So basically is what you learn in IGCSE, so I'm not going to repeat again. Elastic collision, inelastic collision, and explosion. For elastic and elastic, it depends on whether or not Ke will conserve or not before and after the collision. While for explosion is basically talking about for a kind of collision that has zero momentum at the first place, and then it just explodes into maybe 2 or 3 pieces. And I think for the equation, you should know momentum equals to mass times velocity. This is basically like the fourth one. For the last one, I think you rarely use it, and actually you can just prove it by yourself if you look at the item carefully. So for the first question, it's very simple. I don't think I need to explain anything, and here is a workout. Basically, you just apply the equation of F equal change of momentum over time. Next question is again very similar and very easy as well. So for impulse, it will be changing momentum, and you just plug in all the number. Be careful that -3 should be put here because it's the opposite direction. Consider as a velocity. And lastly, don't forget to put down the correct unit. You can put down kg times meter per second, or you may put down Newton times second as the unit. For the next question is a very typical IGCSE question that you have seen before. Basically, you apply the conservation of momentum and you substitute the variables that you know. Pay extreme carefulness on the direction which are opposite in velocity here. Here I also make a mistake here that I thought, I actually overlooked this, and therefore this one should be negative, and therefore I make the wrong answer here. Instead it should be 0, and therefore the common velocity will be 0 at last. And therefore this is a case where the kinetic energy basically is 0 after the collision. For the next question is about a ball rolling on the horizontal floor hitting to the wall with certain angle and bounce with certain angle as well. So you can see from the diagram it's clearly shown already. You are pretty lucky that it's 45 degrees, so that no matter you take sine or cosine, it's basically the same. So I will expect you to draw 2 components for the velocity. Shown here, horizontal one and vertical one. For horizontal one, which is in orange color, you can see that there are no difference before and after collision. For the green one, which is the vertical one, you can see that they are basically opposite. And therefore, if you only calculate the change of momentum, you can just consider the vertical one, vertical velocity, and of course don't forget to times the mass afterwards, and you should be able to find the answers of 1.41 with the correct unit. And don't forget that it should be away from the wall for a direction, because the question asks you about direction, and you know momentum is a vector as well. For part B, it's rather tricky, and it's actually a very typical question as well. For all students learning in momentum, you should really consider this when you learn this. Say in this situation, whether or not the momentum is conserved here. I assume you have already done it, so I'll now show you the answer. And your answer actually could be both yes and no, or you choose one side and explain with the correct explanation. If you say the momentum is not conserved here, you can use the answers that you calculate from part A, saying that the change of momentum is not zero, and there is also external force, so that external force acting on the ball, which is an impact force, and therefore the momentum of the ball would not be conserved. But usually I would prefer to say in the second version, saying that the momentum is conserved, because I'll prefer to say momentum is conserved, so that the whole system and idea is still valid. But anyway, if you say momentum is conserved here, you should say that if we consider the ball, the wall, and also the planet as a whole of closed system, and therefore the impact force I just mentioned, that means the impact force that you have around here will be just an internal force only. So in that case, the change in momentum will not be affected. If you consider the momentum gained by the wall and the planet as well, there should not be any difference. So the momentum should be conserved at last. For the next question is again very simple. You just apply the conservation of momentum m1u1 plus m2u2 equal to m1v1 plus m2v2. It's just too simple that I don't even want to do the substitution work for you. You just do it yourself. You should be able to find the answers as what you can see from the textbook, which is 7. Make sure you indicate the direction as well. For the next question, for part A, asks you to find the impulse of the force, and you should clearly know that from the graph, which is force against time, the impulse, which is change of momentum, will be represented by the area over here. And therefore, you can just calculate the area under the graph with the usual way you calculate for trapezoid, and you should be able to find the answer as 88. I checked the answers on the textbook. I think it said 92. I think is that. I checked I checked 3 times actually on the graph, and I don't think I made any mistake here. So the answer should be 88 instead, with the correct unit kg meter per second. For part B, it said if the speed of the mass at 15 seconds, find the speed when the mass is at 15 seconds. So basically what you do is you apply the equation of changing momentum, and since 15 seconds is just the end of the graph, so you can use the answers from A, and therefore you can use the equation and find velocities as 22 meters per second. Basically C is the opposite. Say that, well, if it's separate from B, so say it's saying that if it was brought to rest at 15 seconds, so what was the initial velocity in that case? So I think the answer should not be 22. Again, it should be negative 22. So at last it will kind of gain 22 meters per second, so that the final velocity will become 0, which means rest at last. So that's the idea. For the next question is again very similar to the previous one. For part A, asks you to find the speed of the ball after 4 seconds. So what you're gonna do is, again, you need to acknowledge the area for the force against time. That one, the area are the impulses, and therefore for the total area, because the question said is after 4 seconds, and therefore you want to say the total area instead. So the impulse will be calculate all these 3 rectangular shape area. So it's 150 kg meter per second. And therefore, if you use this, because this is the impulse that you get, that means a change of momentum, and therefore it will equal to mv and therefore you can find the velocity by yourself, which is I think did I do it here? I think I didn't do it here, so you can still calculate by yourself. Should be 6 at last. For part B, for the graph, you want to show the variation of the boy for the speed with time. Basically, you look at each of the area of the impulse that you gain. You will know that every time he just gain, kind of like gaining 2 meters per second over that 0.5 second, like each of these. And therefore, the graph for the VT graph, oh, I forgot to put down the word V. VT graph will look like this. A lot more like I don't know how to describe, like a staircase. Well, not really a staircase. It's more look like this anyway. For the next one is, it looks pretty hard for part A, right? Because it asks you to prove, kind of like proving an equation. So what you're gonna do is, there's no diagram, so you want to draw a diagram. So here is a diagram. The ball go downward, and the time of impact, that means change of time, is t given by the question. And after that, the ball goes up again, and the highest point you can reach is h2. So what you're gonna do is, you need to look at the equation that the textbook wants you to prove over here, and clearly you can see that is something about energy actually. Or you can know that, oh, since there's no other way you can do it, so the only thing you can consider is energy. And by conservation of energy, KE convert to GPE. So for this one, there is GPE, and now when you go to bottom, it gain KE, right? And again, after the collision, you have certain KE, and it will change to GPE as well. But notice that for the first GPE and first KE, it does not mean they are equal to the second KE or second GPE. Of course, there should be some kind of energy loss to, well, not really loss, but transfer to the other form of energy during the collision. But anyway, you should know that by conservation of energy, KE change to GPE, in this situation, you should find out that the velocity will be equal to square root of 2gh. And therefore, you can know that the time, the velocity before the collision and after collision, u and v here, they can be represented by square roots of 2gh, respectively, respective h of them. And after that, it's very clear already. By applying the usual equation for forces equal change in momentum over time, you just plug in v and u over there, and you should be able to find, well, since the u, you find u and v are in opposite direction, and therefore you should add a negative sign over here, and therefore you can get a plus, like what you can see in what they expect here. However, I truly believe that, again, your textbook has a typo here. It should not be 2, it should be t instead. There's no way that you can get rid of the t and you can get a 2 figure here. Okay, so that's for part A. For part B is really simple. You look at the equation that you prove, you derive in part A, and you just sub it all, and you can find the answer. The next question is more about concepts rather than calculation or proving anything. So it said that there is a ball moving vertically and hit the horizontal floor. Normally, that means 90 degrees with certain speed. But anyway, so the diagrams look like this. It's very similar to the previous one. V1 go down and V2 move up. And therefore, one thing that you should notice is something different from the previous question. Previous question, it asked you to prove the net force. And while this question 80 here, it asks you to show the average force acting on the ball from the floor. So if you compare the question wording, it's a bit different. So the answers will be different as well. As you can see, there are something is an extra term of plus mg here. So this one is actually came from the fact that if you draw the free body diagram of the ball, when it is at the spot where it's impacting with the ground, of course there are still weights. At the same time, there will be the reaction force. That means normally if you put a ball on the ground, there will still, you always have reaction force, right? Which is counteracting the weight. At the same time, since you want to change the velocity of the ball, well, I mean naturally change the velocity, and therefore there will be a separate force, what we call many times as impact force, acting on the ball. So for the reaction force, they will give you mg. So this is contributed by the reaction force, and while this part is contributed by the normal impact force, as what we do many times in this chapter. And therefore that is how it looks like. For part B, it said a fine expression for the average net force. In this case, you can get rid of the mg in this case. For the next question is very simple again. For part A, asks you how long the spring is in contact with the ball. So if you look at the graph, you can see it start at 0.5 and end at 1.5. So the difference is 1.0 second, which is the time which is in contact. For part B, it asks you to estimate a change in momentum of the ball. So basically, it's very simple again. You look at the area of this. Unfortunately, it's a curve. It's not. I mean, it's not a straight line here, and therefore you can't really calculate it directly. That's why it said estimation here. So I would say you may use a triangle to estimate, and the textbook said the answer is 50 units, which is 50. Well, not fs. I make a typo. It should be ns, Newton second here. And I do believe that if you use a triangle and calculate it as 60, it's still fair enough to do this estimation. For part C, the average force exerted on the ball will be just directly recall the equation. For 82, it's a case that where again you need to draw some diagrams so that you know clearly what happened. So first of all, you got two masses which are held in place with a spring compressing between them, and after that the spring is released. So the 2 kg one will move to the left side with 3 meters per second, while the ball with the 4 kg one, of course, it will move as well. It won't be held in place and not move at all, and therefore it's an unknown velocity as well. Anyway, so before the spring is released, you should know that the energy that they contain and they store inside is the elastic potential energy in the spring. And after that, this energy is converted into the kinetic energy, ideally kinetic energy of that two objects. And therefore, through this, you should know that the momentum is still, of course, conserved here since there's no external force. So you should be able to find that the velocity of 4 kg one is negative 1.5 meters per second. After that, using these two velocity, which is 3 and also 1.5, you should be able to use the equation simply 1/2 mv squared to find out the Ke of each of them respectively. You add together, so you know that's the energy stored in the spring. Ideally, of course, will be 13.5, which is closer to 14 joules, since 2SF should be taken here. Again, this is very ideal because there could be some other energy got transferred, like as if to thermal energy as well. So it won't be really 13.5 joules at last. The last question, it looks very not typical, but in fact it's still the very similar questions that you have seen before. It's basically something we said at the beginning for explosion. So what it means is at the beginning they have no velocity, and after that the whole object basically split into two parts. So for this one, it's very usual that we talk about rocket and the fuel that they burn, and of course the way they burn the fuel is to push the particles backward so that the main body of the rocket can accelerate forward. In the question, it only asks you how much fuel must be burned in that second, to be more precisely, for the first second. So therefore, if you want to say average acceleration of 15.5 meter per second square acceleration for the first second, which basically means the velocity go from 0 to 15.5 meter per second after that 1 second, simply. So by the conservation of momentum again, since the momentum should be 0 at the beginning, and therefore after that should be 0 as well. And therefore you can see that the mass after the explosion will be 5,000 minus the mass of the gas, I name it as m underscript g over here, times 15, since this is the velocity after that second, it gained 15 meters per second, plus the mass of gas times negative 1500, since it said that's the speed they gain, and of course it's going backward, and therefore you can see, you should expect that there is a negative sign here so that the equation can be calculated correctly. And last, you should be able to find the step until it is 5,000 equal to 101 times the mass of the gas, and you should be able to find the answer as 49.5 kg, and that's the answer. Before we end the video, I want to talk about one more thing, is all these questions just now we have came across does not reflect the whole picture of momentum in the syllabus. Especially if you try to recall the study guide, there is something called elastic and inelastic collision. And do remember that usually it's a very simple idea that for elastic, for the KE, they do conserve, they completely 100% conserve for the KE, kinetic energy, before and after the collision. While for elastic, they would not conserve the kinetic energy. So there will be some KE transfer to other kind of energy. And usually you will see that it's talking about two objects and they will stick together afterwards. And for momentum, for both of them, they will be conserved. And that's why we introduce the system of momentum, and therefore you can, as physicists, we can predict more situation, especially when the time that energy does not work for us. Thanks for watching and have a good day.